finding the absolute extrema. So I asked you to determine if you could use EVT or not. So in number one, part A, we say that we can use EVT because it is a closed interval. The function is continuous on that closed part of the interval. Therefore, we can check the endpoints, and we see that at endpoint 0, we have an absolute min. At -2 in the middle, you have an absolute max. And at -4, we are also at 0, so it is also an absolute min. Part B fails EVT because it is not a closed interval. Therefore, you are not guaranteed absolute extrema. And part C also fails because 3 is not in our domain. Our function cannot be 1 through 3. Number 2, find the extrema of the given function on its interval -1 to 3. So once again, we find our derivative. We check our interval to make sure it's continuous. We know it's closed based on the brackets, and it is in fact continuous on that endpoint. And then we have two critical points at 1 and 0. Now at 0, it does not exist on the derivative, but it does exist on the original, therefore it can be an extrema. So we check our endpoints, -1 and 3, as well as our critical points, and we find our absolute max and our absolute mins. Number 3 is a rules theorem. So we are checking to see if there are any points at which f prime of c will equal 0. Since it is continuous and differentiable on the given intervals, and the endpoints are equal to each other on that interval, by Rolle's theorem, we are guaranteed there exists a c value in which our function will equal 0 and have an extrema on the original. So f prime of x is equal to -x² plus 6x minus 3 all over -x plus 3 quantity squared. And then we set that equal to c and solve, and we get that c is approximately 0.5505. From the quadratic formula, we also get 5.449, but that's not in our given interval, therefore it does not count. Number 4, it says apply the mean value theorem to the function on the indicated interval to find all values of c that are guaranteed by the mean value theorem. So we have our given function. We are going to look at the function and we can tell that it is a polynomial. Therefore, it is continuous and differentiable. Since it is continuous and differentiable, the mean value theorem says that there is some point c such that f prime of c equals f of 1 minus f of -1 all over 1 minus -1. So we find the slope of the secant and get that to be -1. We set -1 equal to our derivative of f prime. So by the mean value theorem, -1 has to equal 3x² minus 2x minus 2. And you could have had 3c² minus 2x or minus 2c minus 2 so that you saw these as the c values. And you can actually see I ended up changing that because we always say f prime of c. And we get that c is equal to 1 and -1/3. And both of those are in my interval. Therefore, they are both values that guarantee the slope of the secant equals the slope of the tan. Number 5, we have to apply the mean value theorem on the indicated interval. So we check for continuity, we check for differentiability, we find the point at which the secant equals f prime of c. So we need our derivative, and we need the slope of the secant, which is -1 over x squared equals -1. And then we solve, and we get x equals 1 in this interval. So again, you had 2 c values, but only one of them is in the interval. So the answer to number 5 is 1. Number 6. Okay. And this is really what we're moving on and into today, is questions like number 6. Can we find where it's increasing? Can we find where it's decreasing? We already know how to do this based on that chart I gave you way back in chapter 3, but now we're going to look at it after having evaluated critical points and our mean value theorems. Okay. So before I move on to the second half of the handout, which is kind of like a free response question from AP, are there any questions on what we just went over for 1 through 6? All right. So for the next part, we are looking at a data table. We're looking at a data table with time and velocity. So it's important to recognize that this is velocity, not position. And we get asked a couple questions. So the first question is there a time during the interval where the particle is at rest? So in order to determine if a particle is at rest over an interval, we need to know 2 things. Is this function continuous and differentiable? We are told in the statement above that the velocity is a differentiable function, and you need to recall that differentiability implies continuity. So if a function is differentiable, then it is automatically continuous. Differentiability without continuity. So again, differentiability implies continuity. Continuity does not imply differentiability. So once we know it's differentiable, we know it's continuous. And then for a particle to be at rest, it means our velocity needs to be 0. So what we can do is say by the intermediate value theorem, since the velocity is negative and it's negative at time 0, and the velocity is positive, which it is at time 2, by the intermediate value theorem, there is a time from 0, and you could say all the way up to 12. Could have even said 0 to 2. They would accept both for an AP answer, but we are guaranteed because of this piece of information. Okay, guys, well, I'm not muted because I'm connected on my iPad. For whatever reason, the school computer hates my home Wi-Fi, so bear with me. Okay, so that's answered A. Answer B says, let A of t denote the acceleration of the particle at time t. Is there a time at which it is guaranteed? So this question now is a little bit different because we want to know A of C. Now, I used rule or MVT, but you could have also used Rolle's theorem. So this is where Rolle's theorem comes into play because you're being asked if it's equal to 0. Now, again, either one will work. So we are once again looking at the given information, which is that the velocity is differentiable. Because velocity is differentiable, we know it's continuous. By mean value theorem, we then can say that there is a point at which the derivative, aka acceleration, is equal to the slope of the secant. So we want to look at our data and try to find a time where my data is going to have a slope of 0. And if you think about Rolle's theorem says that f of A equals f of B. So if you look at your data table, where are my velocities the same? Well, they're the same when velocity is 5 here and here. Therefore, that's kind of your application of rules. So, or it's going to give you that slope of 0. So therefore, by MVT, there is a guaranteed time, t equals c, such that A of c equals 0. And again, I know your numbers are a little different. Yours is like your 8 because I added this to your review. So then the next one is the graph below represents the velocity in feet per second of a particle moving along the x-axis over the time interval from t equals 0 to t equals 55. Is there guaranteed time in that interval such that the velocity is equal to 0? So we're only looking from 30 to 55, where my velocity is negative. So velocity is not differentiable because at t equals 40, you have a corner. Therefore, MVT does not apply. So since MVT does not apply, you're not guaranteed that the derivative will equal 0. And then you also looked at 4.1. You looked at the extreme value theorems of a function handout. So this handout says if a point is a relative min, is that point a critical number? So a lot of math in calculus is about being able to justify and reason as to why something is or isn't true. So I really like this handout because the question seems simple, but the thought and process behind them is a little less simple. So we have this first statement, and the answer is yes. If a point is a relative min, is it a critical number? And the reasons for that are if it's a min, then its derivative must be 0 or dne, and by definition, that point is a critical number. Number 2 is also yes. Now, number 3 is where it begins to get a little bit tricky. Number 3 says if a point is an absolute max on an interval, is the point a critical number? This is a case of a maybe, because we know by the extreme value theorem that an endpoint can be an absolute max, and an endpoint by definition is not a critical point. So that's where that maybe sort of comes into play. Okay. Give you guys a second to look at 4, 5, and 6. So again, here's those maybes coming into play because of critical points, open and closed intervals, etc. Number 6, your graph could look different from my graph. The only things that have to match on all of our graphs is that our interval goes from -2 to 5. Sorry, I missed that. And that we have these kind of tidbits of info. Now, again, your characteristics could be a little different than mine. Maybe your absolute max is at a little higher point. Maybe it's at a little lower point. Maybe you don't have, a sharp cusp. Maybe you have a corner, or maybe you have a vertical tangent. But you need to have at 1 something that's not differentiable. Okay? So that kind of goes over everything we did yesterday in class. So what I want to do now is review all of these theorems. So we are going to do a quizzes.